Okay, welcome back to C467. This is our last lecture, which is also the second series of the deep foundations design, and we focus on talk about the settlements or the displacements of deep foundations. So the learning objective for this lecture is to understand pile displacements from three different sources: the sine frictions, the toe bearing, and also elastic compressions. And we will talk about how to plot the the pile load settlement curve, and also we will introduce a very comprehensive analytical method, which is the TZ method for pile settlements analysis. For the reference, part of the material we cover in this lecture is presented in chapter 20 of your textbook. But beware that the TZ method, the textbook didn't talk too much about it. But we will spend a fair amount of time to cover this in this lecture as the last topic of this class, and a little bit more in-depth, more advanced study in the topic of geotechnical engineering design. So what is a settlement in piles? So there's a couple terminology or a couple concept we need to be aware of. So when you have deep foundations, so this is your pile, and when we talk about settlements, is the amount of displacements that happen at the head. So at the head of your foundations, this is the settlement. So this is happening at the pile head, and along with the piles, you will have different amount of settlements. Displacements. So this is a very important concept. So this displacement number 1 versus displacement number 2, and difference. So the settlements at the head will not be equals to the displacement at like certain depth of the piles, and along the depth of the piles, the displacements are different. Why that happens is because the piles that you have is not like a perfectly rigid material. It could make up of concrete, or you could make up with steel, and we know that there could be elastic and plastic compressions that happens on the piles. So especially like maybe hard for you imagine, because you have for example, you have a steel piles. You very hard for you to imagine that the piles got deformed, but in fact ignore the fact that it's just inside the soil, inside the ground. If you just load the piles maybe on compaction machines, actually you will deform, and especially like the piles need to support like a structural load that goes to very high amount of loading. We talk about like 1,000 kips or even more over there. So that's why under structural loadings, the pile can deform, and the amount of deformations depends on the depth. The more material that you cover, like like the deeper going the piles, the piles along the different locations, you expect that the amount of elastic compressions is different. So that's why along different locations, you have different displacements, and it's kind of important for us to figure that out too, or account for it, because at the end of the day, the settlement at the head depends on the settlements along the pile, and also very important, the settlement at the toe, or the displacements at the toe of the foundations. So those, and it's not just like a purely the pile material. It's not just the concrete behavior or steel behavior. It's also involve the the reactions between the soil and the pile. So there's like a soil structure interactions. This fancy terms, we use a lot in engineering for advanced design. So it can be very complicated because you're dealing with the behavior or the interactions between two very different materials, and all those come together will give you the settlements at the head you want. So the settlements would be equals to the sum of displacement along the piles plus the elastic compressions of the pile. So when we talk about settlement, which means the downward movement at top, which means at the pile head. That's where the locations we connect to the structure columns, right? So at the head of the piles, you represent how what kind of like structural movement you expect, and the displacements. So the pile displacements means that the downward movement at some point in the pile. So this could be a little bit. This could be different. Actually, this is different than the settlements at the head. So those terminology and those concepts, you need to we need to visualize it before we further go into this topic. So when explicit like a settlements analysis is necessary, so again this can be a quite complicated topic, and compared with like the previous like topic that we talk about in this class, this start getting to the graduate level when we talk about the pile settlements. Because again, like you involve like a soil structural interactions, and the TZ method we talk about will be a comprehensive engineering analysis to how to capture the response of soil structural interactions, and we will get there. So when we need such advanced analysis, for example, when you have a pile group, or the structure is sensitive to settlements such as like hospitals or nuclear plants, you have very important structure that cannot tolerate any kind of movement, or like superior this cannot tolerate as much. It's less forgiving in terms of like structural displacement due to the ground settlements. So maybe also you have a large portions of nominal capacity come from the toe bearing of the foundations on compressible soil. So if you have a soft clay, you have soft soil layers, you expect a lot of settlements. So you need to perform settlement analysis for the deep foundations. Also, when you have very long piles, this is tricky because when you have long piles, it means more elastic compressions from the pile material. So you expect quite a bit of movement that may damage your structure. Also, when you have a very high compressible strata, especially at the toe, so the toe movement, the toe displacements, is important too. And for DZ analysis, you have very different like a whole separate terms that using a spring try to capture the toe movement. The down drag load, so this is due to the consolidations of soil. So if the soil is consolidating, you would drag down the pile. So this is like a graduate level topic we will talk about in C567. By the way, C567 will be offered next semester, graduate level class. So if you're working professional, or if you're graduate students, or like even you're senior students, you want to continue on the topic of geotech design, you can sign for this class next semester. And as a senior student, undergrad senior students, you can take this course, take a 5,000 level course to substitute one of your 4,000 level course requirement. If you're interested to go that way, let me know and I can arrange the paperwork for you to claim the credit. But anyways, like the C567 is kind of like a continuations of this course. We talk more a little bit more further into advanced geotech design. Also, we will try to teach you how to use some of the available commercials computations software package flag. I will try to teach you how to use a finite difference computation package to do geotech design in C567. So if you're interested in that class, I highly recommend you to take it next semester, since just finished this class this semester. So it would be nice to have the continuations to pick up the next class. And this is a class that we only offer every 3 semester. But anyways, so that's a down drag loads, and also when the static load test, and also maybe like a pile, dynamic piles, like a driving test is not conduct, so you don't have the field data. You may want to perform this type of analysis. So that's very important to know how to do this and when we need to do this. And again, we talked about in the last lecture, any like a field data will be much appreciated to those like analytical approach we are doing here, because field data are more site specific, and also both site specific and also the pile specific for your project. But again, good data come with a cost. So those field testing is not cheap. Or you may work on on a tunneling project that you want to study the impact of your tunneling process, impact on existing structure, or any kind of like a construction you're doing. You want to know about your construction's activities, how it affect the existing structure nearby, or a tunnel boring machines you're driven by underneath it. There's no way you can go back to the site to do a field test anymore. Or it would be too much to do to cover tunnel alignments. Talk about 10 miles, 20 miles. It's just too much for you to cover to have like a site-specific test, for each structure. Then those analytical analysis is a must. So it's quite common for us to geotech to do those kind of analysis. But keep that in mind. As a geotech engineers, you need to understand what is the best approach for your project or for your design you're working on. So in summary, there's 3 components for this pile settlements analysis, or like the settlements at the head, the pile head. It comes from 3 parts. First, the side frictions settlements, plus the toe displacements, and also plus the elastic compressions of the pile. So that's a 3 part we need to work on. Okay, let's talk about those size frictions. And that's analytical model that will help us to visualize, or help us to at least to see what is happening when the pile, the deep foundations is settling, and again, like we have three components, right? The previous slides we talked about the side frictions, the total displacements, and also elastic compressions. But now just look at the first item, side friction. So we will talk about those three items individually. So let's first focus on the side frictions. And we take advantage of one existing model, the Chin's hyperbolic model, which the reference is the Cook 2009. So let's talk about this model. So you help us to see what happens at the side of the piles when settlements or displacement occur. So when, first of all, when we talk about hyperbolic model, it's mathematical functions. So is the model form is y equals a over b plus x divided by c, and a, b, c are kind of like the shape parameters or some constant. So you kind of like control the shape of the hyperbolic model. So you will get a curve like this. So it kind of like the stress strain curve that we have when we talk about soil strain response, right? About the stress strain curve that you get from direct shear tests or unconfined compression tests back into your 360H lab. But anyways, so this curve here will be like the settlement curve we talk about at the side of the foundation. So that's why this model, they adopt the shape, and ABC are the are the constant that will change the shape of the curve. So keep that in mind. This is where we get to this kind of like mathematical functions. And the Chin's hyperbolic model is this one. So the side frictions times the side area is equals to the side displacements divided by a constant plus the side displacement again times the nominal frictional force. So this will be kind of like in the model, this is kind of like the y, and here is kind of like the x. So that's the hyperbolic model. So those are these two terms. There are the size displacements. Kind of like the x terms, and here is the side frictions. In a pile segment. Which means like, when we have a piles, so when we have a piles, what we do is like we break down the piles in different segments, and each segments you will have your own like side area, right? So you have your own side area, and then you get the side frictions, and each segments you will have a curve to represent the pile displacements. So this could be the frictional force, and then this is the side displacements. So each segments of your piles, you will have its own displacement curve. So you realize now this is like a soil pile interactions. So it's not just like a single number that you calculate. And of like, is we talk about the response of the piles, and it depends on the interactions between the frictions and the displacements, which means if you want to calculate the displacements at certain point or certain like a segments of your piles, it depends on how much frictions it has mobilized. So if you have mobilized more frictions, then you expect more displacements. So the whole thing you think about, like, the piles when you put into place, or the piles kind of like in actions, the displacements of the piles, at least just the sign frictions, actually is both like the three components. The displacements of the piles will depends on how much loading you're adding on the piles. So that's why, like, this is no longer just like a material response. This is kind of like a stress strain response. Now is the soil structure interactions response. So that's why you have multiple curve to represent the side frictions. The rest of it, this Ks is the side resistant flexible factors. And here is the nominal friction force, like we calculate in the pile capacity in the previous lecture. And the K sub S is equals to M sub S times the pile diameters B right there, and the F sub N divided by A sub S. So this is the pile diameters. And M sub S is a constant. It's kind of like the modulus of the soil correction factors. So that's why this is pile structure reactions, because this K sub S bring in this M sub S, which is as parameters to describe the soil response. So this is like a response 001 for stiff or hard soil, and this will be equals to 004 for stiff or loose soil, and this will be equals 0.005 for rock. So it a little bit like it depends on the material, the soil, that contribute to the displacement response. And this K sub S actually it can like represented by a graph. So if you plot the normalized side frictions versus the side frictions displacements there, the initial slope of this curve is the K sub S. It's a side frictions size resistant flexible factor. And at the end of the day, like, if we plot out the curve here, that's the side friction settlement curve. So this is the side frictions or displacement curve. So if we want to find out the displacements, so this is what we want to find out. It depends on how much frictions it has mobilized. So it depends on the side frictions. Okay, next is the toe bearing. So we move on to the second components for that contribute to the overall settlements of the piles. And again, we use the hyperbolic model again. So the genes hyperbolic model. Again, the same reference. The Cook, 2009. So this very similar permutations. You take advantage of the mathematical model. Now the toe bearing is equals to the displacements at the toe times divided by correction factors plus the displacements at the toe again times the nominal capacity at the toe. So this is the toe displacements, and this part is the nominal net unit toe bearing capacity, and the y terms or the fun terms, the terms on the left hand side is the toe bearing capacity, toe bearing. And this KT turns here, so this KT turns, oops, is the toe resistance factors, and this is equals to 0.54 divided by the E25 times B, and the E25 is equals to M times QC, and the QC is the CPT values. And for the M factors, it depends on the soils and also the pile. So this is the M factors, depends on the two. So that's why this is a soil pile or soil structure interactions, because you can capture the two with this like M factors here, which is the toe resistant factors. So at the end of the day, again, you have your part. Oh, let me just do the same thing here. So again, like you have the piles at the toe. You have it another like a displacement response depends on the toe bearing. So this is the toe bearing. You will get a curve again. So how much displacements that will take place at the toe of the foundations depends on how much toe bearing capacity it has mobilized. So this two slides, slide number 3 and number 4, I just want to give you an idea of what's going on when a piles that is being loaded. So when you're being loaded, you imagine it's not like a simple single response. You at least you have 3 different components of response. So the curve that here, oops. So the curve you get here will be very different than the curve that you get elsewhere. And the whole thing is complicated in a sense that this is a soil interactions. And if we want to find out the total settlements at the head, we need to toggle each of them individually. And slide 4 and 5, I want you to give you an ideas through Chin's hyperbolic model, which is It's not very popular because there's a better method to use, which is a TZ method. I will talk about next. But this like a hypermodic model I want to start with because this is simple compared with the DZ method, and at least like you can see the math, you see the equations, even though it's just a model, but give you an idea what's going on and how the response curve look like. So I don't think I will focus on this like a Chin's model, but at least like hopefully get you start to think about what really happening when this pile is settling. So again, like the displacement that you get from the top, very top at the head, you make up with like a different parts, and we just talk about the first two, the side frictions and the toe displacements. And the third one that we're going to talk about is the elastic compressions. So the theoretical mathematical relationships, or like the derivations of elastic compressions is the summations of the loading divided by A, which is the area, times the elastic modulus, and sum of all the segments, sum of the whole length. So that's why, like at the beginning, like we talk about the pile settlements. You become a concern when you have a very long pile, because if you look at this mathematical equations here, if you have very long piles, then you have you times you sum up all the length, then end up like then you will have a large elastic settlements at the end of the day. So that's why like you care about pile settlements when you have a very long compressible pile. And it matters, even though you thought like metal is so hard that like rarely deform. Yes, pile metal is stiff compared with soil, so you won't like compress much, but you only compress a bit. But like you have very long pile, especially when we talk about 50 feet of pile, 70 feet of pile, and you sum up of all this little by little, like small elastic compressions, end up like it could be significance that give you structural damage when you collect to the column of the structure. So that's why something at least you need to look at as a geotech engineers for foundation design. So this is the mathematical derivations of elastic compressions for material. So you will capture and this is not like also, I want you also to able to see this. Since this is just the material only, which means like steel or concrete only, so you will capture by the elastic modulus parameter there for the material behavior. Versus like the sine frictions and the toe bearing, you are talking about the response or the interactions between the soils and the piles at the side, and also the soil and the piles at the toe. So so that's why, like at the end of the day, you need a curve to represent the response, because now we not only one dimensions, is very likely like a multi-dimensions behavior response. So that's why it's complicated. You need to have a curve to actually just to describe what's happening. Versus here now we just deal with one single material, steel or concrete, and you can use one parameter as the modulus to capture the whole behavior. So this delta E is the settlement. At the top of the piles, due to elastic compressions. So you're lowering from the top, and if you sum up the whole length of the piles at the top of the piles, you got the elastic compressions components of the settlements, of the overall settlements. The P here is the compressive force, is the pretty much is the structural loading adding on the piles. And the area is the cross-sections area of the piles. The E is elastic modulus. And Z is the depth below top of the pile. So again, when you have your piles, so here is the elastic compressions at the top. So here at the head of the piles, and if you sum up all the little segments through the depth of the piles, then you add them up, you will get the total elastic compression settlements. Again, that's just one of the 3 components for the total settlements to have. So that's just the elastic compressions of the pile.